you nuke that exam out of the water. I have been teaching physics for 45 years and ever since I got back from my mission. And I've never had more than 15 perfect scores on an exam before. So this is unprecedented. This is just really impressive how many of you totally mastered this material. And what this chart doesn't really show is that, well, it does a little bit. These are the, you know, the people that got 100%, the people that got 96, you know, there's just as many, a little bit more. And so we really have a huge number of what you could consider perfect scores. I still have a couple of individuals who need to take that exam because they were out of town. And so I have made a video of the solutions, but I haven't posted it yet. If you could give me another day or two before I post that, that would be wonderful. Would someone be willing to give us an opening prayer this morning? Anyone feeling in the mood?
Heavenly Father, we're thankful for this opportunity that we have to come to physics and to learn more about my world. And we're thankful for Professor Francis and for this exam that he's given us. And please bless us that we'll feel the Spirit and that we can continue to learn and go forth and serve. And we say these things on the Father in the name of thy Son, Jesus Christ. Amen.
Amen. Thank you, Jameson. I appreciate that. Okay. We've got a lot of fun things to do today. Magnetism is just one of the most exciting topics in physics. This was in our newspaper in Bozeman many years ago, before many of you were born. There was a guy called the Unabomber that was sending out bombs and letters, and it turns out he was doing everything from a little shack not far from where we live. And so this was a cartoon in the paper that I used to represent the nuts and crazies that were sometimes hidden up in the hill. What are magnets anyway? That's our goal today, is to understand what makes a magnet. Last day, if you'll remember, we were talking about Newton's third law, and that if I can exert a normal force on you, you're exerting a normal force on me. And in this case, we're talking about a magnetic force. If a moving charge can experience a magnetic force, then a moving charge should be able to create a magnetic force. And that's the famous result of Ørsted's experiment. You remember that he was giving a lecture, and although almost never does something good happen during a lecture, this time it did. He happened to have a wire nearby hooked to a battery, and found that his lodestones lined up in a circular way. Now, we found that if we had a long straight wire or piece of anything really that was charged electrically with too many electrons or too few electrons, that we got an electric field that was radially symmetric. The lines went either radially out evenly spaced, or they came in radially spaced. And that's because of symmetry. If I look at a long straight wire, it looks the same whether I'm looking this way or standing on my head or tilting my head 30 degrees. And so the answer has to look the same. Well, the same thing's true with magnetic fields, except that there's a caveat. And that is that magnetic field lines always close on themselves. They don't start on anything like electric field lines. They don't end on anything like electric field lines. they close on themselves, they're loops. And so the only kind of field line that has the same symmetry as that wire is a circle, a circle. Now, we used a right-hand rule, and we're going to explore the use of that right-hand rule in this week's tutorial. I call this right-hand rule number 2, and wait, there's more. We'll get to that in a minute. But here we're just using our right hand as a memory device, kind of like tying a string to our finger to remind us to bring bread home from the store, okay? I got a straight part of my right hand, I got a curved part of my right hand. The straight part is going to represent the straight wire, the current in the straight wire. And when I say current, of course, I mean conventional current. The curved part of my hand reminds me which way those magnetic field lines circle around that wire. Now, if I look at this wire that has conventional current going to the right, if I use my right-hand rule, number 2, and put my thumb in the direction of the current, what I find is that above the wire, at that dot there, my fingers are pointing out of the page. And so that's the direction that the magnetic field would point. On the other hand, if I look below, and if I look up there, I also get out of the page. If I look down here, again, by right-hand rule number 2, my fingers are pointing into the page. And again, here. Now, this side view doesn't really give me any information about magnitude. So let's look at an end view. And by end view, you see that current's coming towards me, which means I've got my eyeball right here looking at that wire as the current's coming right towards my forehead, okay? And what I find is that up here, put my thumb in the direction of the current, the B field is to the left. And this is the new part. If I look up there, it's still to the left, but what I find is that it's weaker. And that shouldn't surprise us, okay? That shouldn't surprise us. Now, down here, my right-hand rule is telling me that the magnetic field is to the right. And again, the further away, the weaker it gets. Now, a result that we don't really have the math background to prove, and then I'm not going to use it in any of your homework or exams, because I figure if you didn't prove it, if you didn't build it yourself, you don't fully trust it, okay? Yeah, Greg told me it was true, but yeah, what's that gonna buy you, okay? This is true, I just can't prove it today. That twice as far away from a wire, the magnetic field is going to be half as strong. Now, that's very different than the electric force for a point source. You remember that twice as far away, it was 1/4 as strong. Well, this only depends as 1 over R, not 1 over R squared. Now, if I were to draw a magnetic field line, it would be this green circle. And that means if I wanted to know what the magnetic field looked like here, it would be straight up, tangent to the circle. If I wanted to know what it was like here, it would be straight down, tangent to that circle. If I wanted to know what it was here, it would be up at 45 degrees, tangent to that circle. Check on your neighbor. See if your neighbor understands the magnetic field due to a long straight wire. Okay. Now, folks, in your homework and on the next exam, there are going to be a whole lot of problems where you're trying to figure out what magnetic force is being exerted by object A on object B, okay? And as you solve those problems, the most important step is recognizing what you don't care about, okay? There's all sorts of things in your life that, you know, you don't care that much about, okay? And things that you care deeply about. Now, for example, if I have these two current carrying wires carrying current in the same direction, if I were to ask, what is the magnetic force on wire one? Well, it turns out that wire one is making a magnetic field, and that magnetic field, if I use right-hand rule number 2, goes into the page on this side, out of the page on that side. It wraps around. Let me get a visual here. Okay, if this is the wire, it's gonna wrap around like this. The same thing's true for this one here. It's gonna wrap around like this, okay? They both make magnetic field, but I don't care about both of them, okay? If I'm looking for the force on wire one, I care about the magnetic field created by wire two. Wire one's not pushing on itself, it's being pushed by wire two. Now, what does the magnetic field look like due to wire two? Well, the current's going up, so it goes into the page over there, it comes out of the page over there. I know what it looks like everywhere in the room, but I don't care. I don't care what it is over there. I care what it is right here where it's doing the pushing, okay? And so I care there, okay? And if I use right-hand rule number 2, right there, the magnetic field due to wire 2 is out of the page, out of the page. I just use right-hand rule number 2. Now, we only have one right-hand rule that gives me the force, the actual push or the pull. And you remember how we use that. The force we find by reaching in the direction of the flow, the motion, and then I turn my wrist so that I can wave in the direction of the B field. And that gives me the force. Okay? Does everyone see how I got that force? Now, if I wanted the force on wire 2, I could just use Newton's third law and say, well, if 2 pulls 1 to the right, then 1's going to pull 2 to the left. Bada bing, bada boom. Okay? Or I could just do the whole process over again. If I'm looking for the force on 2, I only care about the magnetic field created by wire 1. And if I look at that magnetic field, again, I know what it is everywhere, but I only really care about what it is right over there where it's doing the pushing. Okay? And over there, by right-hand rule number 2, it's into the page. Okay? Now that I have the magnetic field, I can find the magnetic force by right-hand rule number 1. I reach in the direction of the flow. I turn my wrist so that I can wave in the direction of the B field, and I get a force to the right. Okay? Now, I can demonstrate this with this wonderful demo that Clark has provided. We have it set so that the current is going the same direction in both of these wires. And I'm going to push this button and pray that I've set it up correctly. This is predicting that these will attract each other. Okay? 1, 2, 3. I think that's an attraction. Okay? So physics works. I love it. Okay. Now in in Montana, this is, I mean, we're simple folk, and this is the demo that we have, it's hooked to a 12-volt battery, and anyway, Clark often worries about me not turning things off, and just let him know that once while I was lecturing, this thing started smoking just because, okay? Now, what if they're going in opposite directions? Okay, let's do the same thing. If I want the force on wire 1, again, I know the magnetic field due to both of these wires, but I don't care, okay? It's only 2 that's pulling or pushing on wire 1. So I want the magnetic field due to wire 1. Now, by right-hand rule number 2, that's going to, I set it down, I shouldn't have. By right-hand rule number 2, that's going to make a circle around like this. And again, I don't care what's happening over here. I care what's happening right there where it's doing the pushing. And right there, it's into the page. Okay. Well, now that I've got the magnetic field over there, I can get the magnetic force by right-hand rule number 1. I reach in the direction of the flow. I turn my wrist so that I can wave in the direction of the B field, and I get a repulsive force like that. Now again, if I wanted the force on wire 2, I could use Newton's third law, or I could do the whole thing over again. I could find the magnetic field due to wire 1 at the location of wire 2. Now, wire 1 has current going up, so the magnetic field lines are going to wrap around this way. Okay, and I don't care what they're doing over here. I care what they're doing over here where wire 2 is. And over there, they're going into the page. Okay. And now I reach in the direction of the flow. This is a little hard because I'm short. Okay. And I turn my wrist so that I can wave in the direction of the B field. And that gives me my force away. Now, on this wonderful device here, there's a little switch that says, make them anti-parallel. And then you've got to manually change this. Okay. And now when I push the button, they should fly apart. And 1, 2, 3. Ha 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 ha. I love physics. Questions on that? Check that your neighbor's just overwhelmed with excitement. Okay. Over and over again, we're going to review the right-hand rules. And so let's kind of go through them real quick. Right-hand rule number 1 is the only one of the right-hand rules that will give me an actual force. If I'm looking for an actual push or a pull, it's right-hand rule number 1 every time. Okay. I reach in the direction of the motion, whether it's a particle that's flying through the air or whether it's current that's flowing through a wire. I reach in the direction of the motion. The most important step is turning your wrist so that you can wave in the direction of the B field. Your right thumb is going to be in the direction of the force if it's a positive charge. Now, we had this problem in the homework, and a lot of us were struggling to get the right answer. And that's because you were plugging in the wrong angle, okay? In this problem, we had a, let's pretend that that's east, okay? It's not, that's north, but we're just gonna put ourselves in this, in the frame of reference of this slide where Canada, we're gonna make believe is that way. And so the magnetic field is towards Canada and down. And I'm gonna put my left arm in the direction of that magnetic field. We were told that the particle was streaming east. If that's north, that's east, and that the particle was going parallel to the floor. Now, the angle that we want to put in this formula. No, sorry. That's not. I'm sorry. Okay. Temporarily close things up. The angle that we want to put in that formula is the angle between the velocity, that's my right arm, and the magnetic field, that's my left arm. Now, if I hold my arms like this, what would you say that angle is? 90 degrees. Now what is it? 90 degrees, yeah, okay, 90 degrees. And so we have to put 90 degrees in there. Now, it turns out that the sine of 70 degrees is 0.94. And so if you were using 70 degrees instead of 90 degrees, you were oh so close. And you were tempted to say, oh, I just have a rounding error here. Oh no, you have an understanding error. Okay, now on your exam question, and I promise you, you're going to have one of these problems. You're going to see those field lines again. Okay, and the most important step is figuring out that angle. Okay, if the particle's traveling towards the ceiling, that angle is going to be 90 plus 70 or 160. If that particle is headed south, parallel to the floor, that's going to be 90 plus 20 or 110. Okay, you have to be able to see what that angle is. Now, some of you can see in 3 dimensions. You close your eyes and you can visualize where everything is. I'm not one of those people, but maybe you are. If you're not, bring props, bring pipe cleaners or something when you're doing your exam or your homework so that you can visualize things in 3 dimensions. Now, when I plug in, I'm looking for the magnitude. It's a proton, it's positive anyway. There's the elementary charge, there's the speed, there's the strength of the magnetic field, half a Gauss, and the sine of 90 degrees is, of course, 1. Now, I get that very small force, but it's acting on a proton, so it's going to have a great big effect. Now, the direction, again, I'm looking for a force, so I use right-hand rule number 1. I reach in the direction of the motion, that's east, and then I turn my wrist so that I can wave in the direction of the B field, that's down 70 degrees, and my thumb is going to be pointing in that direction there. And that would be the force acting on that proton. Please check on your neighbor again, see if they got that right. I reach in the direction of the motion, that's out of the page. I turn my wrist so that I can wave in the direction of that blue vector, and my thumb is pointing in the direction of the force.
Oh, right hand. Oh my gosh. Oh my.
Yes. Oh, the blue lines are representing the magnetic field of the Earth. The magnetic field of the Earth, here where we live, points towards the north. This is really north, and down 70 degrees, because the field lines come out of the south pole of the Earth where the penguins live and go down into the North Pole where Santa Claus works. And we're close to Santa Claus. Okay, So they're coming down where we live, okay? So right-hand rule number 2 is a rule to find the magnetic field, not the force, the magnetic field. And you remember the field is what causes the force. Okay. Now, in this week's tutorial, we explore the magnetic field due to a loop of wire. And rather than starting with a circular loop of wire carrying current, we started with a square so that we could use our right-hand rule number 2 for a straight wire. Now, if I have this wire carrying current, and it looks like that current is going to the right on the bottom and to the left on the top. And so if I look at the magnetic field due to the top, I put my thumb in the direction of the current flow. Above the wire, I've got into the page. Below the wire, I've got out of the page, like that, okay? Now, if I look at this wire here, the current's going down this wire, and so that means outside of the square, I've got into the page, and inside the square, I've got out of the page. Again, if I look at this one here, inside the square, I've got out of the page. Outside the square, I've got into the page. And then finally, this one here, outside I've got into the page, and inside I've got out of the page. Now, what you're seeing is a loop with a whole lot of field lines coming out the middle and coming back outside, okay? Remember, these field lines have to close on themselves, so they're coming through the middle and then wrapping around to come back around for another pass, okay? Now, if I were to look at this on the side, it would look like they were coming through the middle and then wrapping back around. It would look, let me rotate that this way, okay? And what I would see, let's pause here for a moment. What is that? What is that? Okay, well, if the current on top is going this way, and I rotate this 90 degrees, what direction is the current on top coming now? Towards you, okay? Whereas down below, the current was going to the right. If I turn this by 90 degrees, that's going to be going away from you. And that's what we're trying to represent with this. At the bottom, the current's going away from you. At the top, it's going towards you. Now, when you see this representation, it should make you hungry, okay? It always does me. What you should think of is a donut, okay? And what we're showing you is a current loop, but only half of the current loop. What we're doing is we're breaking that donut and as a cutaway and just showing you the back half, okay? But you're supposed to be thinking about the whole donut, okay? It's just a representation of, so that we can see which way the current is going around the donut. Okay, tell your neighbor that you'd like a donut. I've been on a diet for a year. I was looking for that excuse to stop by Reams on my way to work today. Yeah. Sugar high. Okay. Now, remember, the field lines were coming out the middle, and then we turned it on its side. And so that means that the field lines on the outside are going back, and in the middle, they're going to the right. Now, we've seen this magnetic field before, okay? If I have a bar magnet, I get magnetic field lines that come out of the north and then wrap back around and go into the south. And that's one of the most important tools to put in your toolbox, is that when we have current going around in a loop, it generates a magnetic field that looks all the world like a bar magnet, okay? And what that means is that we can identify, if I have a current carrying loop, we can identify a north side of that loop and a south side of that loop. And I can pretend that that loop is really just a little bar magnet. And the direction of that north pole is given by your right hand. It's so handy, okay? This time I use the curved part of my right hand to represent the curved current in the loop. And my right thumb can tell me two things. It can either tell me the direction of the magnetic field in the middle of the loop, or equivalently, it can tell me which side of that loop is the North Pole. Either one of those is useful, right? And so we call that right-hand rule number 3. And just like right-hand rule number 2, it's a rule to give me the field, not the force, the field. Now, it's really easy to remember. When the current's straight, use your thumb to represent the current. When the current's going a loop, use the curved part of your right hand to represent the loop. I was working with a young man during tutorial years ago, and I was trying to get them to understand the right-hand rules. And this young man, he just was sitting there at the table and, you know, nodding and letting other people do all the work and everything. I said, young man, unless you do this, you are never going to understand. And that poor young man lifted up his arm and he had no right hand. And I said, okay, left-hand rule. We're going to learn a left-hand rule. I was mortified. I really was ashamed of myself. Okay, so if I have current going around in a loop, I get magnetic field lines that look all the world like what we've seen before. The magnetic field due to a bar magnet. And so every time I see a loop of current, this is important. Every time I see a loop of current, I use my right-hand rule number 3 to replace that loop with a bar magnet. And then, listen to this, I pretend I'm in the 2nd grade, okay? Because once I've turned it into a bar magnet, I know how bar magnets act with each other. I've known that since the 2nd grade, okay? So, we'll practice that in a moment. If I showed you that visual right there and asked you which side of that loop is the north side, tell your neighbor, which side of that loop is the north side? That's good. It's not easy. It's kind of confusing. Kind of depends on how you're viewing that. And that's why we're always going to draw those current loops this way. Because this way, this is ambiguous. This is non-ambiguous. This tells me it goes in at the bottom, it goes up the back, and it comes out at the top. And my right thumb is pointing to the right. And so think of that as a little compass needle. And the arrow is the north-seeking pole of the compass needle. The north pole of the bar magnet. Okay? Now, the Earth has a magnetic field that looks all the world like that of a bar magnet, where the field lines come out of the south geographic pole and come in near the where Santa Claus lives. And so the question is, what creates that magnetic field? And we're not entirely sure, but the best theory that we have right now is some sort of what do they call it? Dynamo? A dynamo effect. We've got a flow of molten material that circles the Earth around the equator, carrying charge. And the question is, if I think of that as a current loop, which way would the current have to flow to give me a bar magnet like that? Would it have to go from east to west or from west to east? Would it have to go from the Boston side of the United States to San Francisco, or from San Francisco to Boston? Tell your neighbor what you think it would be. Okay. Remember, you want the North Pole to be represented by your thumb. And so if your thumb's pointing down towards the penguins, the current, conventional current, is going to have to flow from east to west, from Boston to San Francisco, and something like that. And here I represented the part of the loop that was closest to us with a heavier arrow. A heavier arrow. Now, we just talked about a single loop, and we found that it acts like a very, very short bar magnet. If we have a lot of loops, and we call that a solenoid, what we find is that by superposition, we get a magnetic field that looks like a long bar magnet. A long bar magnet. Okay, now, I've got a demo here. Let's see if I can make it work. We've got a solenoid there, and I'm gonna bigger that, okay? And I put some iron filings down on the glass, and I'm going to put a current through that solenoid. At the same time, I tap the glass to allow things to move. I might have put too many iron filings on there, but you're starting to see that field that looks like that. Okay. Now, I can also demonstrate that this a solenoid acts like a bar magnet with this demo here. I've got a solenoid that is hanging and free to swivel. Oh, wrong. Okay. And when I put a current through it, what I find is that I can put a little bit more current through it. I can get it to rotate, just like if I had another bar magnet on a pivot, I could make this thing rotate by essentially pushing and pulling with different poles. And that's what I'm doing here. Okay. Now, so what we find is that a bar magnet looks like a solenoid, or a solenoid looks like a bar magnet. But why? But why would they act the same? Well, let me see if I can help you understand that. Suppose I had you all stand up and gave you each a tennis ball. And each one of you represented an atom of iron. And each of you as an atom of iron could be represented as a little current loop. A little current loop that has its own magnetic dipole. Okay? Now, if I could get you all, everyone in the room, to rotate the same way with your little tennis ball, with your charge, representing my current loop, okay? If I look down on this class from above, it would look like this. We'd all be rotating clockwise. All of us are rotating clockwise, all the same. Now, those are little current loops. But if I looked at one location, let's say I looked right here. Well, this tennis ball is going down and this tennis ball is going up. This current is going down, this current's going up. That's going to cancel. If I look here, this current's going to the left, this current's going to the right. That's going to cancel. If I look at a corner, this one's going up and to the left, this is down to the left, this is down and to the right, up and to the right. Those are going to add up to 0. But if I look at the edge, if I look right there, there's nothing to cancel it. And so that looks like I have a current there. And here, it looks like I have a current. And here, it looks like I have a current. And here, it looks like I have a current. And here, and here, and here, and here, and here. You're getting tired of this? I am. Okay? And there. Now, nothing is actually flowing all the way around. None of our tennis balls get all the way around the room, okay? But if this represented a bar of iron, where I could get all of the dipoles of the iron lined up so that their current loops were all rotating the same way, it would appear that current was going around that bar of iron. There's nothing that gets from here to here, but it looks like there's current there, and it looks like there's current there, and it looks like there's current there. So what that bar of iron looks like when it's magnetized is that, like a solenoid. And we call that the magnetization current. The magnetization current. Now, how do they get lined up? Okay. How do they get lined up? Why are they lined up in the first place? Well, if I have a current carrying loop, it experiences a torque, a twisting force that we talked about in Physics 105. And we just witnessed over that demo over there. A loop produces a B field that looks like that from a magnet. I know that a magnet will line up with an external magnetic field. Does a loop react to an external field like a magnet? And the answer is yes. If I have this magnetic field, the blue field lines are going towards the piano. If I have a loop in that magnetic field, the first thing I do is replace that loop with a little bar magnet. Well, I let my fingers go in at that side and out at that side. That means this is going to look like a little bar magnet with a north pole here and a south pole there. A bar magnet that's free to rotate looks like a compass needle. And that's going to line up with this magnetic field like that. Okay? So if I can take a bar of iron and put it in a strong magnetic field, I can get all of those little dipoles with each of those iron atoms to line up with each other so that they're all spin in the same direction. Now, I've got Clark yesterday searched all over and found these pieces of soft iron here, and you see that they just don't pick up. They don't pick up these paper clips at all, okay? But if I put it on that strong magnet and just tap it a little bit. Now, it's a magnet, okay? I was able to line that up. Now, something just fell. Oh, my bar. Okay, now, how can I demagnetize this? Well, anyone that has been in charge of a lab at a university or a high school knows the answer to that. You just drop it, okay? If you drop it on the floor enough times, you get things messed up. Or if you put it into a strong magnetic field that's in the opposite direction, you can get the field to change direction. The other day, we found that one of our compasses was actually pointing towards Mexico, and that's gonna, you're gonna end up in the wrong place if you follow that compass, okay? Now, another way to demagnetize this would be to heat it up. As you heat something up, you put random motion into the atoms, and they start jiggling. And if you get above a certain temperature that we call the Curie temperature, which is different for different materials, then you break that symmetry, you break that alignment of all of the dipoles. Now we're going to take a different approach. We're going to demagnetize this by putting it in a magnetic field that changes 120 times a second. Back and forth, back and forth, back and forth. And I'm going to do that with this little AC alternating current supply. And so I put it in the middle of this solenoid. And so the magnetic field in the middle of the solenoid is going this way and then that way and then this way and that way, changing direction 120 times a second. And if I just jiggle that a little bit to let the atoms kind of go where they want to go, and then turn that off, what I find is that it's still a little bit of a magnet. Let's give it some more. Okay. What do you think, Clark? Should I turn it up? Where are we at?
Full of fuse, huh?
Can't take much more, Captain. Okay. Okay. Okay, we have not demagnetized it. That works. I know that this, I shouldn't admit this with Clark there, but in Boston, what I would do is hook that to an AC source that was 120 volts, and then it really, but that's not safe. Don't do that at home, okay? So let's talk about magnetizing it with a DC source. Here I've got a bar that is not a magnet. If I take this this solenoid and hook it to a DC power source so that I always have current running the same direction, so the magnetic field is always the same direction, Now, what I'm going to get is a strong magnet, okay? Let me see if I can demagnetize this puppy. Okay. Hey, look at that. Huh, Greg did it. That's demagnetized, okay? Now, there's another way to magnetize a rod, but it's very, very ineffective. And that is to line the rod up with the Earth's magnetic field, which would be towards Canada and down 70 degrees, and just whack it for all you're worth, okay? And if you do that hard enough, you can actually magnetize it a little bit, but that's not the preferred method, okay? Now, where were we? Keeping it all straight, okay? I've given you a lot to think about. 3 right-hand rules, there's a magnetic field, there's a magnetic force. Let's see if we can all just put it together so that it makes sense, okay? We organize our understanding. We are treating this magnetic interaction as a 2-step dance. The first step of this 2-step dance is that something creates a magnetic field, sets up the magnetic field in the room. Now, there's 3 ways that we've found so far to set up a magnetic field. And so I would like to make sure that we understand those 3 ways. The first way is with a bar magnet. And I'm going to represent the magnetic field in blue. And we know that those magnetic field lines come out of the north, wrap around and go into the south. Out of the north, wrap around and go into the south, okay? And so when I'm dealing with a homework problem or on the exam, if I'm looking for the magnetic field near a North Pole, I take that to be away from the north. And if I'm looking for the magnetic field near a South Pole, I take that to be towards the south, okay? Now, the second way is with a solenoid. And a solenoid, I represent with a whole bunch of donuts, or half donuts, if you will. And if I want my North Pole to be on this side, I've got to have the current coming out on top and in at the bottom. Now, we found that the magnetic field due to this solenoid comes out of the north and wraps around and goes into the south, but then it keeps on going. And the field lines close on themselves. They come out of the north, they wrap around and go into the south, and then they close on each other. Now, what that means is that outside of the solenoid, the field lines are going from north to south. Inside the solenoid, they're going from south to north to complete the loop. And what that also tells me is that inside a bar magnet, where I can't see, where I can't put a compass needle to actually measure the direction, my gut tells me that those magnetic field lines are running from south to north, okay, to complete the loop. Check on your neighbor, see if your neighbor is doing okay. Okay. The left case is a long straight wire. And if that current is coming out towards you, the magnetic field lines are going to be circles that are concentric about that wire. Okay? And the direction of that magnetic field at any point is given by right-hand rule number 2. Okay? And that's going to be this way, this way, this way, this way, this way, this way, that way, that way, that way, that way, that way, that way. Okay, so this direction here was given by right-hand rule number 3. Okay, now, once we set up the magnetic field, there are 4 ways that objects can be pushed by that field. So let's talk about those 4 ways. Okay, the first way is a charge moving in a field. If I have some test charge that is moving in some direction in a magnetic field that is in a different direction, and this magnetic field could be created any one of those 3 ways, okay? This angle we're going to call theta, and the force is going to be QBB sine of theta, and the direction is given by right-hand rule number 1, okay? And in this case, if it's a positive charge, that direction is going to be into the page. The second way is a current carrying wire. Again, if I have a magnetic field created one of those 3 ways that looks like this, and I have some current carrying wire that's making an angle of theta with respect to the magnetic field, what I find, I did not derive this for you and we're never going to use it, but the force magnetic per unit length, let's say that this wire has a length L. That's unfortunate. I need that space. Is going to be equal to the current times the B field times the sine of that angle theta. Now, the last 2 ways involve forces on bar magnets. If I have a bar magnet in a uniform magnetic field, and I can tell that that's uniform because the field lines are parallel to each other, I can think of the force as the North Pole being pulled in the direction of the field and the South Pole being pulled in the opposite direction. And so what that's going to do, that's going to cause that, I'm gonna do that in green. That's gonna cause the North Pole to go this way, the South Pole to go this way, and it's gonna line up with the field. And then I'm gonna have a force on the North Pole and a force on the South Pole, but they're gonna cancel each other because they're the same size. Now, if I have a magnetic field that is not uniform, so it's strong here and it's weak here. And this might be something, say, near a big South Pole. Well, if I put a bar magnet down there, again, I'm going to have a force on the North Pole in the direction of the field, force on the South Pole in the opposite direction, and that's going to cause this to rotate and line up like this. But now we've got a different situation than here. Now the North Pole is seeing a strong magnetic field, so it feels a big force to the right, and the South Pole's in a weak magnetic field, and so it's got a smaller magnetic force to the left. And so this thing will be sucked over. And you know that's what you would expect. If I put a little bar magnet next to that great big South Pole, it's going to swing around to the north, aim in the south, and then it's going to slide across the table. Now I can demonstrate that. I can create a magnetic field in this solenoid, and with this power supply, and I've got this. This is just iron, it's not magnetized at all. But when it gets into the presence of this magnetic field, it will become magnetized. And watch what happens when I push the button. Okay, so let's see that again. Got to get it in there a little bit. Okay, now, I was telling Clark just the other day that turn off the power. At the University of Washington, we had a great big huge solenoid. It was enormous. And we had 10 12-volt batteries all hooked in series, so it was 120 DC. And we would get DC current going through this great big solenoid, and we had a great big iron plug that was enormous, and it would go racing into the middle and just stay there. Well, it didn't take long before we geeks figured out that we could push the button on the power and get this thing racing in, and as soon as it got in, we'd turn off the power and it'd race out the other side, and it was a rail gun, and we could fire this down the hall. That was not good. Yeah, that was not good. Now, why would this be useful, this what you see? Well, if you know anything about cars, you know that every now and again your starting motor goes out. But usually what really goes out is the solenoid that sits on top of the starting motor. It gets stuck, and then you got to replace the whole starting motor. Well, it turns out that if it's just stuck a little bit, you can go out and just kind of bang on it with something metal and get it unstuck. But the reason there's a solenoid on your starting motor is that in order to get your car to start, you need to drive about 75 amps through your starter. Now, I'm here to tell you that if you've got a 16-year-old child learning how to drive, you don't want 75 amps going through the steering column where you put in the key. That's just not good. And so what we do instead is we hook the battery to a solenoid on top of the starting motor. And we put the switch where you put the key, the ignition, in this circuit here. And in that circuit, when we close the switch by turning the key, we only put a small flow, 0.5 amp, something that's not going to hurt your child, okay? And then that current through the solenoid does what we just saw. It pulls in that iron rod, closing that switch so that we can now create the 75 amps in a circuit that doesn't involve your child, okay? Now, folks, in the 37th chapter of Alma, verse 6, it says, "But behold, I say unto you, that by small and simple things are great things brought to pass." Okay, it's the small and simple things that we have to do, like pray and read our scriptures and go to the temple, that brings the real power, the power that's way beyond us and our ability to get things done and to bless the lives of others. So that's not going to be on the exam on this planet, but it will be on a different exam. Okay. Now, get your clicker out. Before I let you go to devotional, and the devotional speaker today is Michael Dunn. I just want to tell you that when I was being interviewed for this job at BYU, the very first interview I had was my wife and I had a Zoom interview with Michael Dunn, and it was just the most wonderful experience. I left that feeling like I was actually worth something. You know, he was so kind and so Christ-like. I am looking forward to his talk today. So, what direction is the force on the right loop? These two, this one's fixed in place. This one's free to move. Is this going to go to the left, to the right, up, down, or just stay put? With your clicker, let me get you started. Okay, now you can click. Okay, last call. Get her done. Is that all of us? Okay, we're not sure. Okay, we're really not sure. Because B is not the right answer. Okay. You've already forgotten my key advice for this lecture, and that is whenever you're dealing with a current loop, use right-hand rule number 3 to replace it by a bar magnet and then pretend you're in the 2nd grade. So if I replace this loop with a bar magnet, that's the north side there, okay? If I do the same thing with this loop, with right-hand rule number 3, this is the south pole. Now imagine putting these 2 bar magnets on the table and asking, what's that going to do if I hold this one in place? Well, the south pole is going to be attracted to the north pole, and it's going to race to the left. So the correct answer was A. Okay. Now, one more clicker question. If I put this bar magnet that's free to rotate about that orange dot, if I put it there next to this current loop, will it pivot clockwise or counterclockwise with your clicker? Okay. Last call. Okay. Okay, good. We're doing better. Again, we use right-hand rule, number 3, to look at the, again, it's all about what you don't care about, okay? The current loop's making a magnetic field, the bar magnet's making a magnetic field, but I don't care about both of those. The magnet's not pushing on itself. I care about the magnetic field due to the loop, and we know by right-hand rule number 3 that in the center of the loop, it's going to the left. And if I think of that as a little compass needle, that's going to line up with that magnetic field. And so the answer was counterclockwise. Okay, folks, go get a good seat at that devotional and listen to Elder Dunn.